Tonight, we're going to slowly drift through 100 facts about space-time, the strange fabric that holds every planet, every star, every memory, and every moment together. Some of these facts will sound impossible at first, but the universe does not have to make sense in the same way everyday life does. You do not need to remember everything tonight. Just let the ideas pass by, one at a time. And before we begin, leave a comment down below with something you would like to fall asleep to next. Now, get comfortable, take a slow breath, and let's begin. There is no universal version of right now. It feels natural to believe that the whole universe shares the same present moment, that somewhere there is one giant cosmic now. But relativity says that is not quite true. Two events that seem to happen at the same time, for one observer may not seem simultaneous, for another observer moving differently. This matters most when the events are far apart. For example, two flashes of light on opposite sides of a moving train could be judged as simultaneous by someone standing beside the tracks. But a passenger moving through the middle of the train could disagree about which flash happened first. Neither observer is broken. Neither one is imagining things. They are simply slicing space-time into moments differently. The universe may not have one shared present after all. Moving clocks really do run slower. This does not mean a clock physically gets tired or begins malfunctioning. It means time itself passes differently when two observers are moving relative to each other. The faster that motion becomes, the stronger the effect becomes. At everyday speeds, it is far too tiny to notice. A person walking across a room does not suddenly age slower in any meaningful way, but at speeds close to light, the difference becomes enormous. A traveler on a very fast spaceship could experience years, while much more time passes for people who stayed behind. From inside the spaceship, everything would feel completely normal. Their heartbeat would feel normal. Their thoughts would feel normal. Their clock would tick normally. Only when the clocks are compared, later would the difference become clear. The twin paradox is not actually a paradox. Imagine identical twins. One stays on Earth. The other travels through space at an incredible speed, turns around and comes home. When they meet again, the traveling twin is younger. At first, this sounds unfair. After all, each twin could say the other one was moving, but their situations are not truly identical. The traveler changes direction, turns around, and follows a different path through space-time. The twin on Earth remains in roughly the same frame for the whole trip. So when they reunite, the clocks they carry have measured different amounts of time. The traveler has experienced less of it. It is not magic. It is not a trick. It is the universe quietly keeping track of the different paths each person took through space-time. Some black holes appear to break one of the most important rules in the universe. They seem to send matter moving faster than light. Not almost as fast. Not just incredibly fast. Faster than light itself. At least that is what it can look like from Earth. Near some black holes, enormous beams of particles can be launched outward from the regions around them. These beams are called jets. They can stretch across thousands, sometimes millions, of light years. They move through space at speeds so close to the speed of light that the difference becomes almost impossible to picture. And when one of those jets happens to be aimed partly toward Earth, something strange happens. It can appear to move faster than light. One of the clearest examples comes from the giant black hole at the center of the galaxy M87. This is the same galaxy where astronomers captured the first image of a black hole's shadow. But far beyond that shadow, the black hole is sending a narrow jet of particles out into space. When astronomers watched part of that jet over several years, they saw a bright feature moving away from the black hole. From our point of view, it appeared to be moving more than 6 times faster than light. 6 times. That should be impossible. Nothing with mass can travel through space faster than light. Imagine a bright knot of particles moving through a jet. It is traveling almost directly toward Earth, but also slightly sideways across our view of the sky. At one moment, it gives off a flash of light. That light begins traveling toward us. Then, a little later, the knot has moved much farther forward. It gives off another flash. But because the knot has moved closer to Earth, the second flash has less distance to travel. The second flash is chasing the first one. And because the particle is moving almost as fast as light, it can close much of that gap. So the time between the 2 flashes reaching us becomes much shorter than the actual time between them. From Earth, the motion looks compressed. The bright knot seems to jump across space much faster than it really did. It is not crossing the universe faster than light. It only appears that way because we are receiving its light in a strange order. The universe has not broken its own rules. It has simply tricked our eyes with distance and time. Motion can make light look brighter in one direction and dimmer in another. This is called relativistic beaming. Imagine a flashlight moving extremely close to light speed. To someone directly in front of it, its light would appear concentrated and brighter. To someone behind it, the light would appear dimmer and shifted toward red. At normal speeds, this effect is far too small to notice. But near black holes, particles can be accelerated so close to light speed that the effect becomes dramatic. A jet pointed partly toward Earth can look much brighter than an identical jet pointed away from us. The universe is not always showing us objects exactly as they would look from every angle. Speed changes the way light is aimed, colored, timed, and seen. A black hole can make the universe behind it appear in front of you. Imagine looking toward a black hole, floating against a field of distant stars. At first, you might expect it to look like a perfectly dark circle, blocking the stars behind it. And it would. But around that darkness, something much stranger would appear. A thin ring of light. Not light coming from the black hole. Light from stars that are actually behind it. Normally, that light would travel away from you. It would miss your eyes completely. But near a black hole, space is curved so deeply that light can be forced to bend around it. A beam of starlight can travel toward the black hole, curve around its edge, and then continue outward in your direction. So a star, hidden behind the black hole, could still become visible. Its light would be wrapped around the darkness like a halo. The black hole would act like a gravitational lens, not made from glass, not made from mirrors, just a region where space has been bent so intensely that light no longer follows the straight paths we are used to. There is a region around a black hole where light can curve so sharply that it can travel almost all the way around it. In some cases, light can circle the black hole once before escaping. Other rays can circle it twice. Some can make 3 loops, or more. Each extra trip makes the image fainter. Each extra loop creates another thin layer of light around the black hole's shadow. So the bright ring around a black hole is not always one simple ring. It can contain many overlapping images. Some light may have come almost directly toward you. Some may have been bent around one side. Some may have crossed behind the black hole, wrapped around it, and only then found its way to your eyes. It means that near a black hole, one object can appear in more than one place at the same time. A star behind the black hole may form a glowing circle around it. A cloud of gas can look like it has been stretched into an arc. The distant sky can become warped and folded around a dark center. Imagine that, without an explosion or a warning, the sun was replaced by a black hole. The same mass would still be there, but the bright yellow sphere in the sky would be gone. For a little more than 8 minutes, nobody on Earth would know. The last light from the sun would still be traveling toward us. Daylight would continue. The sky would still be blue. Then, all at once, the final sunlight would arrive. And after that, there would be no sunrise, no warm glow over the horizon, no sunlight reaching the oceans, the cities, or the moon. Just a black hole at the center of the solar system. But Earth would not fall in. It would not begin spiraling toward the darkness. Its orbit would not suddenly collapse. In fact, Earth would continue moving around that black hole, almost exactly as it moves around the sun now. 1 year would still take 1 year. The planets would continue following their familiar paths. The moon would continue orbiting Earth. Nothing would be pulled out of place. A black hole's event horizon is not a solid surface. A black hole is not a hole with a hard edge that you could crash into like a wall. Its event horizon is a boundary, a point of no return. Outside that boundary, light can still escape inside it. Every possible future path leads deeper inward. Not because something grabs you with a visible hand, but because space-time is curved so extremely that escape becomes impossible. The event horizon is one of the strangest boundaries in nature. It is not made of rock, gas, or metal. It is a border written into the geometry of space-time. A place where the future itself points in only one direction. Gravity changes the flow of time. Time passes more slowly near stronger gravity. A clock closer to Earth's surface runs ever so slightly slower than a clock farther away. The difference is tiny. You would never notice it by living on a hill instead of at the beach. But with accurate enough clocks, it can be measured. Near a black hole, the effect becomes far more dramatic. To someone far away, time near the black hole appears to slow down. This does not mean the person near the black hole feels frozen. Their own time still feels normal to them. But when clocks in different gravitational environments are compared, they no longer agree. Gravity does not just bend space. It reaches into time too. GPS works because engineers account for relativity. The GPS on a phone needs extremely accurate time. It works by comparing signals from satellites carrying precise clocks. But those satellites are moving quickly around Earth, which makes their clocks run slower than clocks on the ground. At the same time, the satellites are farther from Earth's gravity, which makes their clocks run faster. Both effects must be calculated carefully. Otherwise, the system would slowly drift out of accuracy. Your phone could begin placing you in the wrong spot. So every time GPS helps you find a store, a house, or a road home, it is quietly using Einstein's ideas. Relativity is not only hiding near black holes, it has helped people navigate ordinary life. At the center of the Milky Way, there is a star that races around an invisible object at more than 15 million miles per hour. The star is called S2, and every 16 years, it completes one enormous orbit around the supermassive black hole at the heart of our galaxy. That black hole is called Sagittarius A star. It has the mass of about 4 million suns. But S2 does not orbit it from a safe and comfortable distance. At its closest point, the star passes less than 20 billion kilometers from the black hole. That may sound far away, but in space, it is incredibly close. It is only a little farther from the black hole than Neptune is from our Sun. And as S2 reaches that closest point, it moves at nearly 3% of the speed of light. For a brief part of its journey, it is one of the fastest stars we have ever watched. Imagine standing on a planet orbiting that star. For most of the 16-year journey, the black hole would be a distant, invisible force somewhere in the dark. But as the star fell deeper toward the center of the Milky Way, the sky around you would begin to feel different. The pull of the black hole would grow stronger. The star would accelerate, and the rest of the universe would appear to shift in subtle ways. Because near a black hole, gravity does not only pull on matter, it affects time. The deeper you move into a strong gravitational field, the more slowly time passes compared with someone far away. Not enough for a person riding on S2 to notice. A clock beside you would still seem perfectly normal. Your heartbeat would feel normal. A single second would still feel like a single second. But from far away, the light leaving the star would change. As S2 passed close to Sagittarius A star, astronomers on Earth saw that light become slightly redder. This is called gravitational redshift. The light had to climb away from the black hole's gravity before beginning its long journey toward us. And that climb took energy from the light itself. The result was tiny. But it was real. It was one more sign that space and time near a black hole do not behave the way they do here. S2 has been watched for decades. Astronomers have followed its path carefully, year after year, watching a bright point of light move through one of the most crowded and chaotic regions in the sky. They could not see the black hole directly at first. They could only see what the black hole was doing to the star. And the motion of S2 gave them something extraordinary. The star was not simply moving in a perfect repeating oval. Its orbit was slowly turning. Each time S2 completes its 16-year journey, the shape of its path shifts slightly. It does not return to exactly the same orbit it followed before. Instead, the orbit slowly rotates around the black hole. This is something Isaac Newton's view of gravity cannot fully explain. But it is exactly the kind of motion Einstein predicted. Space near Sagittarius A star is warped, and S2 is moving through that warped space. So every 16 years, this one star traces a faint, glowing loop around the darkness at the center of our galaxy. It is like watching a single firefly circle an invisible mountain. The mountain cannot be seen. It has no surface. It gives off almost no light, but its presence is written into every turn the star makes. And for us, 26,000 light-years away, S2 has become one of the clearest reminders that black holes are not just ideas hidden inside equations. They are real. They are nearby, at least by galactic standards. And even now, while the Milky Way turns quietly through space, that star is still making its long journey around the darkness at the center of our galaxy. There is a place around a spinning black hole where standing still is impossible. Not difficult, not dangerous, impossible. There is no wind there, no solid surface moving beneath your feet, no visible current pulling you along. And yet, once you enter this strange region, you cannot remain still compared with the rest of the universe. You have to move. You have to circle in the same direction as the black holes spin. This region is called the ergosphere. It exists outside the event horizon, which means escape is still possible. But inside the ergosphere, space itself is being dragged around the black hole. A black hole can spin, not like a planet with a surface, not like a basketball turning through empty space. A black hole has no solid outer shell, but it can carry something called angular momentum. It can inherit that motion from the star that created it. It can gain more spin by pulling in gas, and it can be spun up again when it merges with another black hole. As it turns, it does something deeply strange. It twists the space around it. Imagine placing a spoon into a cup of coffee and slowly stirring. At first, the spoon moves through the liquid, but keep stirring, and the coffee begins to turn with it. The liquid close to the spoon moves fastest. The liquid farther away moves more slowly. Around a spinning black hole, there is no liquid. There is only space, but the effect is strangely similar. The black hole's spin drags the space nearest to it around in the same direction. Far away, the effect is almost too small to notice. But close to the black hole, the twisting becomes extreme. Space begins to behave less like a motionless stage, and more like a river flowing around a dark object. Outside the ergosphere, you could point your spacecraft in any direction and remain still if your engines were strong enough. Inside it, that option disappears. You could still move outward. You could still escape, but you could not hover in place. You could not move in the opposite direction hard enough to cancel the motion of space itself. Every path through time would carry you slightly forward around the spinning black hole. It would be like trying to stand still in a river that has become faster than you could ever swim against. The river is not made of water. It is made of space. And the black hole is not simply pulling you through it. The black hole has made the space around it begin to turn. This effect is called frame dragging. It was predicted by Einstein's theory of general relativity more than a century ago. The idea sounds almost impossible at first. Most of us imagine space as empty, a quiet backdrop where planets, stars, and galaxies move around. But near a spinning black hole, space is not just sitting there. It has shape. It can bend. It can twist. And it can carry things along with it. Colliding black holes can make space-time ring. When two black holes orbit one another and finally merge, they release enormous energy. Some of that energy travels outward as gravitational waves ripples in space-time itself. As a gravitational wave passes through an area, it very slightly stretches space in one direction and squeezes it in another. The effect reaching Earth from distant mergers is unbelievably small, far smaller than anything a person could ever feel. But instruments such as LIGO are sensitive enough to detect it. For the first time, humanity has learned to listen to the universe in a way that does not depend on light. We can detect the faint trembling of space-time caused by distant objects colliding in the dark. Black holes do not always spend their lives alone. Sometimes, two of them find each other. They may begin far apart, orbiting through the darkness like two invisible dancers. For millions or even billions of years, they circle each other from a distance. But every orbit carries away a tiny amount of energy. Not as light, not as heat, but as ripples moving through space itself. These ripples are called gravitational waves. As the black holes lose energy, they slowly move closer together. Their orbit tightens. They speed up. And eventually, the final moments arrive. In a distant galaxy more than 1 billion light-years away, two black holes once began that final spiral. One had about 36 times the mass of our Sun. The other had about 29 times the mass of our Sun. Neither one gave off any light. Neither one could be seen with an ordinary telescope. But as they raced around each other, space itself began to tremble. They moved faster and faster, dozens of orbits every second. Then, in less than a second, they collided. For a brief moment, the collision released an unimaginable amount of energy. About 3 times the mass of our Sun was transformed into gravitational waves, not destroyed, not burned away, turned into motion within space itself. For that instant, the collision released more power through gravitational waves than all the stars in the observable universe release as light. And yet, nothing flashed across the sky. There was no explosion that anyone could have watched from far away. There was no giant fireball. There was only a disturbance moving silently through the universe. A quiet wave in the shape of space and time. It traveled outward in every direction, across empty regions between galaxies, past stars that would never know it had gone by, through clouds of dust, through the darkness between solar systems. And more than 1 billion years later, that wave reached Earth. On September 14th, 2015, it passed through our planet. It passed through oceans, through mountains, through cities, through every person alive at the time. But nobody felt it. The effect was far too small. As the wave moved through Earth, it stretched space in one direction and squeezed it in another. The change was smaller than anything a human body could notice. Smaller than an atom, smaller even than the width of a proton. But scientists had built an instrument sensitive enough to detect it. 2 enormous observatories in the United States, called LIGO, used laser beams traveling through long tunnels. As the gravitational wave passed through, the distances inside those tunnels changed by an almost impossible amount. And for the first time in human history, we directly detected 2 black holes merging. We did not see them. We did not photograph them. We did not hear a sound moving through space. But the signal could be translated into sound. It became a short, rising chirp, a low tone becoming higher and higher. The final signal of 2 black holes spiraling together, colliding, and becoming one. After the merger, the new black hole did not become perfectly still right away. For a brief moment, the warped space around it continued to settle. In a way, the black hole rang, not like a bell made of metal, not with sound, but with tiny waves moving outward through space. Then the ripples faded. The new black hole became quiet, and somewhere far away, in a galaxy we may never see clearly, one invisible object remained where two had once been. A black hole with the mass of roughly 62 suns. The collision was over in less than a second, but its final whisper traveled through the universe for more than 1 billion years, and eventually it reached us. Space and time are not truly separate things. For most of human history, space and time seemed completely different. Space was the place where things happened. Time was the invisible clock that kept everything moving forward. But Einstein's theories changed that picture. They showed that space and time are connected so deeply that it makes more sense to think of them as one thing, space-time. Every object in the universe exists inside it. Every star, every fallen raindrop, every thought in your head, every distant galaxy. All of it has a place in space and a moment in time. Together, those locations and moments form the universe's giant four-dimensional map. Every event needs both a where and a when. Imagine hearing that a meteor struck Earth. You would probably ask where it landed, but you would also need to know when it happened. Without both pieces of information, you would not really know the full event. In physics, an event is anything that happens at one place and one time. A flash of lightning, a supernova exploding, a person opening their eyes in the morning. To describe an event properly, you need 3 directions of space, like left and right, forward and back, up and down. Then you need 1 direction of time. That is why space-time is often described as having 4 dimensions. Not because time is a place you can casually walk into, but because every moment has to be located somewhere in the larger structure of reality. There may be no such thing as absolute stillness. Right now, you might feel perfectly still. Maybe you are lying in bed, sitting on a couch, or resting in a quiet room. But Earth is spinning beneath you. Earth is orbiting the sun. The sun is moving through the Milky Way. And the Milky Way itself is moving through a much larger universe. So are you actually standing still? Relativity gives a strange answer. There is no single universal state of rest. You can only describe motion compared with something else. You are still compared with your room. Your room is moving compared with the sun, and the sun is moving compared with distant galaxies. The universe does not appear to have one perfect place where everything is truly motionless. The speed of light is the same for everyone. This is one of the strangest facts in all of physics. No matter how fast you are moving, light in a vacuum always moves at the same speed. If you shine a flashlight while standing still, the beam travels at light speed. If you shine that same flashlight from a spaceship moving incredibly fast, the light still travels at light speed. Common sense would suggest that the speeds should add together, but light does not work that way. Instead, space and time adjust around the situation. Clocks tick differently. Distances change, but light keeps the same cosmic speed limit. That one simple rule is the reason. Time dilation, length contraction, and many of relativity's strangest effects exist at all. Looking into space means looking into the past. Light takes time to travel. That means nothing in the night sky is seen exactly as it is right now. The moon appears as it was about 1¼ seconds ago. The sun appears as it was a little more than 8 minutes ago. When you look at Jupiter, you are seeing it from tens of minutes in the past. And when you look at the Andromeda galaxy, you are seeing light that began its journey around 2.5 million years ago. That light left before humans had built cities, before written language existed, before our species looked anything like it does now. A telescope is not just a tool for seeing far away. It is also a machine for seeing backward through time. Time dilation has been measured with real clocks. Time dilation is not just an idea from science fiction. Scientists have tested it using extremely precise atomic clocks. Clocks have been flown on airplanes, carried in fast-moving vehicles, and placed on satellites. When those clocks returned, or were compared with clocks that stayed on the ground, they showed tiny but measurable differences. The changes were incredibly small, far too small for a person to feel, but they matched what relativity predicted. This is one of the calmest and strangest things about the universe. Time does not only feel different when life is busy or slow, it can literally pass at a slightly different rate, depending on how you move. The effect is built into reality itself. Fast-moving objects become shorter in the direction they travel. This effect is called length contraction. To an outside observer, an object moving close to light speed appears shorter along the direction it is moving. A spaceship racing past at an extreme speed would look compressed from front to back. But the people inside the ship would not feel squished. Their ship would seem completely normal to them. Their rulers would still measure the same length. Their rooms would still feel the same size. This is because space itself is part of the strange adjustment. Different observers can measure different distances and still both be correct. The universe protects the speed of light by allowing time and distance to behave in ways that feel deeply unfamiliar to us. Cause and effect have a shape in space-time. Every moment in your life has a region of the universe that can affect it, and another region that it can affect. Physicists often picture this using something called a light cone. Imagine a flash of light appearing beside you right now. As time passes, the light spreads outward in every direction. Anything the light can reach lies inside its future light cone. Anything that could have sent light to you before this moment lies inside your past light cone. Events outside those regions are too far away for a signal to reach you, yet this means the universe has a kind of built-in limit on cause and effect. No message, warning, or influence can casually leap across space faster than light. Space and time can disagree, but space-time keeps the score. Two observers may disagree about how much time passed between events. They may disagree about how far apart those events were, but there is still something deeper they agree on, a hidden relationship between distance and time called the space-time interval. It is a kind of combined measurement that stays the same for everyone, even when their clocks and rulers tell different stories. This is one reason relativity does not collapse into confusion. Observers may see the universe from different points of view, but space-time has rules underneath those viewpoints. there is still an underlying structure, a quiet mathematical order, holding every viewpoint together. Gravity is the shape of space-time. Gravity feels like a pulling force. The ground pulls you down. The moon pulls on the oceans. The sun holds Earth in orbit. But Einstein's description is more subtle. Mass and energy change the shape of space-time around them. A planet creates a gentle curve. A star creates a deeper one. A black hole creates an extreme bend in the structure of reality. Objects then move through that curved space-time. What we experience as gravity is often just matter, following the paths created by that curvature. The rubber sheet comparison is not perfect, but it gives the basic feeling. The universe is not a flat, empty stage. It has shape, and that shape is constantly being changed by everything inside it. A falling object is following the straightest path it can. This sounds backwards at first. When you watch an apple fall from a tree, its path looks curved. It goes down toward Earth. But in curved space-time, the straightest possible path is not always a straight line in the way we picture. One physicists call these natural paths geodesics. An object in free fall is simply following a geodesic through the curved space-time around a planet or star. That is why astronauts in orbit feel weightless. They are not beyond gravity. Earth is still strongly affecting them. They are just falling freely around the planet instead of being held up by the ground. Weight is what you feel when something prevents you from following that natural path. Orbiting Earth is really a form of falling. The International Space Station is not floating because gravity disappears up there. Gravity at that altitude is still very strong. The station, its astronauts, and everything inside it are constantly falling toward Earth, but they are also moving sideways so quickly that Earth curves away beneath them. Instead of crashing into the ground, they keep missing it again and again, once every orbit. This is what an orbit really is, a continuous fall around a world. The moon is falling around Earth. Earth is falling around the sun. And the sun is moving through the Milky Way in the same quiet cosmic dance. Falling does not always mean moving downward. Sometimes it means circling forever. Free fall and acceleration can feel surprisingly similar. Einstein had one of his most important ideas while imagining a person inside a closed elevator. If the elevator were floating freely through space, a person inside would feel weightless. But if the elevator were accelerating upward in empty space, the floor would push against their feet in a way that felt very similar to gravity. From inside the elevator alone, it could be difficult to tell which situation they were in. This is called the equivalence principle. It helped Einstein realize that gravity and acceleration are deeply connected. It is one of the reasons gravity became more than a simple pulling force in his theory. Gravity turned into a feature of the geometry of space-time itself. Every clock carries its own path through space-time. In relativity, the time measured by a clock traveling along its own route is called proper time. It is the time that clock truly experiences. Two clocks can begin together, take different journeys through space-time, and meet again having measured different amounts of time. Neither clock is broken. Neither one has made a mistake. One may have traveled faster. One may have spent more time near strong gravity. One may have followed a calmer route. from inside each clock's own world, everything would have felt completely normal. Every second would still have felt like 1 second. But once the clocks are placed side by side again, their readings can be different. Time is not only something that happens everywhere at one identical rate. It is something every traveler quietly carries with them. Tiny particles called muons show that time dilation is real. Muons are created high in Earth's atmosphere when particles from space collide with the air. At rest, a muon survives for only about 2/millionths of a second. That should not be enough time for many of them to reach the ground. And yet scientists detect them here on Earth all the time. The reason is relativity. From our point of view, the muon is moving so quickly that its internal clock runs more slowly. Its short lifetime stretches long enough for it to cross much more of the atmosphere. From the muon's own point of view, its clock still feels normal. Instead, the distance through the atmosphere is shortened in the direction it is moving. Both descriptions agree on the same result. The muon reaches the ground. Time and distance have changed together. Earth gently twists space-time as it spins. Earth does not only curve space-time because of its mass, its rotation has a tiny effect too. As Earth spins, it slightly drags the nearby fabric of space-time along with it. This is called frame dragging. The effect around Earth is incredibly small, but it has been measured with highly sensitive experiments in space, around a much faster and more compact object, such as a spinning black hole. Frame dragging becomes much stronger. Space-time can be twisted around the spinning object, like water swirling near a drain. Even our quiet blue planet is not completely still in the fabric of the universe. It leaves a faint rotating imprint in space-time around it. Gravity can change the color of light. Light has a frequency. You can think of it like a tiny rhythm. When light climbs away from a strong gravitational field, that rhythm stretches out. Its frequency becomes lower, and the light shifts slightly toward the red end of the spectrum. This is called gravitational redshift. Light falling deeper into gravity can shift the other way, toward blue. The effect may sound small, but it reveals something important. Gravity affects not only objects with mass, it affects light itself. Even though light has no rest mass, it still travels through the curved geometry of space-time. And that journey changes the light along the way. Gravity can bend light into strange shapes. When light passes near a massive object, it does not always travel in a perfectly straight line. The curved space-time around a star, galaxy, or black hole can bend the light's path. This is called gravitational lensing. Sometimes it makes distant galaxies look stretched into arcs. Sometimes it creates multiple images of the same object. In especially precise alignments, it can form a glowing ring around the foreground object. A distant galaxy may be hidden behind another galaxy, but gravity can bend its light around the obstacle and bring it toward us anyway. The universe has natural lenses made of gravity, and through them, we can see things that would otherwise remain hidden. Gravity can make a signal take longer to arrive. When a radio signal, laser pulse, or beam of light passes near a massive object, it can take slightly longer to reach its destination than it would in flat, empty space. This is known as the Shapiro delay. The signal is not getting stuck in material. There is no invisible fog slowing it down. Instead, the space-time near the massive object is curved. The signal has a longer and more complicated path to follow. Even light has to obey the shape of reality around it. This is another reminder that space is not just a blank container. Its geometry can influence the journey of anything traveling through it, even something moving as fast as light. The universe expands because space itself expands. When people imagine the expanding universe, they often picture galaxies exploding outward into an empty space beyond them. But the better picture is stranger. Space itself is stretching on very large scales. The distance between faraway galaxies grows because the space between them grows. There does not need to be a central point inside the universe, where the expansion began from many places in the universe. Distant galaxies appear to be moving away. Some extremely distant regions can even become separated from us faster than light, because expanding space is carrying them apart. That does not break the speed limit. Nothing nearby is moving through space faster than light. Instead, the space between distant places is growing. The farther away a galaxy is, the redder its light usually appears. When astronomers study distant galaxies, they do not only see tiny smudges of light. They can separate that light into its different colors, almost like spreading a rainbow across a screen. Inside those colors are patterns that reveal which elements are present in the galaxy. But for distant galaxies, those familiar patterns are often shifted toward the red end of the spectrum. This is called cosmological redshift. It happens because during the light's long journey toward us, the space between galaxies expands. The light wave is stretched along with that expanding space. Its wavelength becomes longer, and longer wavelengths appear redder. So when astronomers see a galaxy whose light has been greatly redshifted, they are not only seeing something far away. They are seeing a message carried through a universe that has changed while the message was still traveling. Distant galaxies are not all moving away at the same rate. On the largest scales, the universe follows a simple-looking pattern. The farther away a galaxy is, the faster it appears to be receding from us. This is known as the Hubble-Lemaitre law. It does not mean Earth sits at the center of the universe. An observer in another distant galaxy would see a similar pattern, with other faraway galaxies moving away from them too. The reason is that space is expanding everywhere. Imagine tiny dots drawn on the surface of a balloon as it inflates. Every dot sees the other distant dots getting farther away. The more space there is between two dots, the more new space can appear between them as the balloon expands. The universe is not exactly like a balloon, but the comparison helps explain why the most distant galaxies seem to be separating from us the fastest. The expansion of the universe does not pull everything apart. It might sound like expanding space should make your room slowly larger, or make Earth drift away from the sun, or make the atoms in your body loosen over time. But the universe's expansion is much too weak on small scales to overcome other forces. Gravity holds galaxies together. Gravity holds solar systems together. Electromagnetism holds atoms and molecules together. The expansion becomes important only across truly enormous distances, between groups of galaxies that are not tightly bound to one another. Inside the Milky Way, stars are not being pulled apart by cosmic expansion. Inside our solar system, planets are not slowly being carried away by it either. The universe can be stretching on the grandest scale imaginable, while ordinary things remain steady, solid, and close together. Your bed is not expanding beneath you. Your heartbeat is not being stretched apart. The cosmic expansion mostly reveals itself in the deep distance between galaxies. Cosmological redshift is not exactly the same as an ambulance passing by. When an ambulance drives past, its siren sounds higher as it approaches and lower as it moves away. That is the Doppler effect. The sound waves are compressed in front of the moving ambulance and stretched behind it. Light can experience a similar effect when objects move through space, but cosmological redshift is stranger. The distant galaxy's light is not simply being stretched because the galaxy is flying through a still empty background. Instead, the space between us and the galaxy expands while the light travels. The wave is carried through that expanding space and grows longer along the way. It is a subtle difference, but it changes the way we picture the universe. The deep red light from a distant galaxy is not only telling us that the galaxy is moving away, it is telling us that space itself has been growing during the light's journey. Distant time appears to pass more slowly because the universe has expanded. When astronomers watch a very distant supernova brighten and fade, they can see something remarkable. The entire event appears stretched out in time, a process that may have taken a certain number of days near the supernova can appear to take longer when we observe it from Earth. This is not because the explosion itself was moving in slow motion. It is because the expanding universe stretches the light signals that carry the event to us. The gaps between arriving waves become wider, and the gaps between arriving moments do too. In a sense, the universe has stretched the supernova's light and its visible timeline together. This is called cosmological time dilation. It gives astronomers another way to see that space and time are linked on the largest scales. Even the rhythm of a distant explosion can be altered by the expansion of the universe. The observable universe is not necessarily the entire universe. There is a limit to how much of the universe we can see, not because telescopes are too weak, but because light has only had a limited amount of time to travel since the universe began. Anything beyond a certain distance is too far away for its light to have reached us yet. The region we can observe is called the observable universe. It is like standing in the middle of a vast nighttime fog. You can see as far as the light allows, but you cannot automatically assume that nothing exists beyond the edge of your view. There may be much more universe beyond our observable horizon, possibly far more than we will ever be able to see. The observable universe is not a bubble with a physical wall around it. It is simply the part of reality that has had enough time to send us information. The observable universe is much wider than 13.8 billion light-years. the universe is around 13.8 billion years old. At first, it seems like that should mean we can only see objects 13.8 billion light-years away. But space has expanded, while the ancient light has been traveling toward us. The galaxies that sent that light were much closer when the light began its journey. Since then, the distance between us and those regions has grown enormously, so the observable universe is far wider than a simple 13.8 billion light-year radius. The oldest light we detect today has been traveling for nearly the entire age of the universe, but the places that released it are now much farther away than the distance light could travel through. A universe that never changed. Space-time keeps stretching the map while the light moves across it. The journey and the distance are not the same thing. A cosmic horizon is not a wall at the edge of existence. When people hear that there is a limit to the observable universe, it can sound like there must be a giant boundary somewhere, a final dark wall at the end of reality, but a cosmic horizon is not a physical object. You would not reach it by traveling toward it in a spaceship. It is more like the horizon at sea. As you move forward, the horizon moves too. The cosmic horizon is the limit of the information that can reach us at this point in the universe's history. Beyond it, there may be galaxies, stars, and enormous structures, but their light has not had enough time to arrive. And because the universe's expansion is accelerating, there are distant regions whose future light may never reach us at all. The horizon is not the end of the universe. It is the edge of what the universe has allowed us to know. Some places we can see may already be beyond our future reach. There are galaxies whose ancient light has reached us, allowing us to see them as they were long ago. But because the universe's expansion is accelerating, some of those galaxies may now be so far away that a signal sent from Earth today would never reach them. Their past has become visible to us, but their future may be forever out of contact. This is one of the quietest, strange facts about the cosmos. Seeing something does not always mean you can communicate with it. The observable universe contains regions whose old light can still arrive here. Yet the future light they emit may be carried away by expanding space before it can cross the distance to us. The universe has horizons not only around what we can see, but around what we may ever be able to influence. The cosmic microwave background is the oldest light we can see. Long before the first stars appeared, the universe was filled with a hot glow, not the light of suns or galaxies, but the leftover radiation from the universe's early, dense beginning. Today, that ancient light still fills all of space. It comes from every direction in the sky, and it is called the cosmic microwave background, or CMB. It is the oldest light that can travel freely to us. When we detect it, we are looking back to a time when the universe was only around 380,000 years old. There were no planets, no stars, no galaxies, no life, just a much hotter, younger universe slowly becoming transparent for the first time. The cosmic microwave background is like a faint afterglow, still drifting through the darkness, nearly 14 billion years later. The early universe was once too foggy for light to travel freely. Before the cosmic microwave background was released, the universe was extremely hot. It was filled with a dense mixture of particles and light. Electrons were moving freely through space, constantly scattering photons. A photon could not travel very far before hitting something and changing direction. The whole universe was like a thick, glowing fog. Light existed, but it could not move freely across long distances. Then, as the universe expanded and cooled, electrons began joining with atomic nuclei to form neutral atoms. With fewer loose electrons in the way, light was finally able to travel across space. That released light is what we now observe as the cosmic microwave background. Anything that happened before that time is hidden behind the early universe's fog. We can infer parts of it through physics, but we cannot directly see farther back using ordinary light. The oldest light in the universe is now colder than deep space feels. When the cosmic microwave background was released, the universe was incredibly hot compared with today. The light had a much shorter wavelength and far more energy. But as space expanded, that ancient radiation was stretched out over billions of years. It shifted from a hot glow into microwave radiation. Today, the cosmic microwave background has an average temperature of only about 2.7 degrees above absolute zero. It is almost unimaginably cold, yet it is everywhere. A faint sea of ancient radiation surrounding every galaxy, every star, every planet, and every person. Even in the darkest empty region between galaxies, that leftover glow is still there. The universe may look black to our eyes, but at microwave wavelengths, the sky quietly shines with the cooled afterglow of its earliest visible chapter. Tiny ripples in the cosmic microwave background became everything we see. The cosmic microwave background is almost perfectly smooth. Almost, when scientists map it carefully, they find tiny temperature differences from one region to another. Some areas were ever so slightly denser than others. The differences were incredibly small, but gravity had billions of years to work with them. Denser regions pulled in more matter. That matter pulled in even more matter. Slowly, clouds formed, then the first stars, then galaxies, then clusters of galaxies. In a very real sense, the entire cosmic web began as tiny wrinkles in the universe's oldest light. The Milky Way may trace part of its history back to one of those ancient, nearly invisible differences. Everything familiar in the night sky grew from a universe that was almost smooth, but not perfectly smooth. There was a time before stars, known as the Cosmic Dark Ages. After the early universe became transparent, there was still no sunlight, no starlight, no galaxies glowing in the distance. The universe was filled mostly with hydrogen and helium gas, along with dark matter, quietly cooling and drifting through space. For a long stretch of cosmic history, the universe was dark. This era is often called the Cosmic Dark Ages. It was not dark because nothing existed. There was plenty of matter, there was gravity, there was the faint microwave afterglow from the Big Bang, but there were no stars yet to shine across the darkness. Eventually, gravity pulled gas into the first dense regions, and somewhere in that quiet, ancient dark, the first stars began to ignite. The first stars changed the universe forever. The first stars were born in a universe with almost no heavy elements. There was no oxygen, no carbon, no iron, no rocky planets, and no familiar chemistry. Those things had not been made yet. The first stars formed mainly from hydrogen and helium. Many were likely much larger and brighter than stars like our sun. They burned fiercely and did not live long. But during their brief lives, they began changing the universe. Their light broke apart neutral hydrogen gas. Their cores created heavier elements, and when some of them died in enormous explosions, they scattered those elements into space. The iron in blood, the oxygen in water, and the carbon in living things all depend on generations of stars that came after those first lights. The universe had to become luminous before it could slowly become complex. The first starlight helped make the universe transparent again. When the first stars and galaxies began shining, their intense ultraviolet light spread through the hydrogen gas around them. That light changed the gas by knocking electrons loose from atoms over time. More and more of the universe became ionized. This period is called reionization. It was another major transformation in cosmic history. The universe had once been a hot fog, then it became transparent and dark, and then the first stars began filling it with light again. The details are still being studied. Astronomers use powerful telescopes to look for galaxies from this distant era, but the basic story is clear. The first stars did more than decorate the universe with light. They changed the state of the gas between galaxies and helped shape the transparent cosmos we see today. The universe may have expanded unbelievably fast in its first tiny fraction of a second. One leading idea in cosmology is called inflation. It proposes that, very early in the universe's history, space expanded at an extraordinary rate for a tiny fraction of a second. This does not mean ordinary objects raced through space faster than light. Instead, space itself expanded. Two regions could become separated from each other incredibly quickly because new space appeared between them. Inflation is still a model, not something we have watched happen, but it helps explain several features of the universe we observe today, including why the universe looks so smooth across vast distances, and why its large-scale geometry appears close to flat. It is strange to think that the calm universe we see now may have begun with a nearly unimaginably brief burst of expansion, a moment so short that ordinary language barely knows how to describe it. Inflation may have stretched tiny quantum fluctuations into galaxies. At the smallest scales, nature is not perfectly still. Quantum physics suggests there are tiny fluctuations even in empty space, short-lived differences in energy and density. During cosmic inflation, some scientists think those microscopic fluctuations were stretched to enormous scales. What began as tiny irregularities may have become the slightly denser and less dense regions seen later in the cosmic microwave background. Then gravity took over across billions of years. Those tiny differences grew into the first structures of the universe. This is one of the most beautiful ideas in modern cosmology. The largest things we know, entire galaxies and galaxy clusters, may trace their origins back to incredibly small fluctuations in the earliest moments of space-time. The universe may have magnified its smallest uncertainties into its grandest structures. The cosmic microwave background gives us a useful reference frame. Relativity says there is no absolute state of rest that applies to every possible situation. but the universe does contain a useful large-scale reference. The cosmic microwave background fills the sky in every direction. If you were perfectly at rest relative to that ancient glow, it would look almost equally warm in every direction. But because Earth, the solar system, and the Milky Way are moving through space, the background looks slightly warmer in the direction we are moving, and slightly cooler behind us. Scientists can measure that tiny difference. It tells us how we are moving relative to the average expansion of the universe. This does not bring back an absolute universal rest frame in the old-fashioned sense, but it gives cosmologists a natural way to describe motion on the largest possible scales. The age of the universe is measured using cosmic time. When people say the universe is around 13.8 billion years old, they are describing something called cosmic time. It is the time measured by clocks that move along with the average expansion of the universe. You can imagine it as the universe's broad shared timeline. From the early hot state, through the formation of atoms, stars, galaxies, planets, and eventually us. But cosmic time does not erase relativity. A clock moving at extreme speed, or sitting near very strong gravity, can still measure time differently from that average cosmic clock. The age of the universe is not a magical stopwatch floating outside reality. It is a useful way of describing the history of an expanding universe from the viewpoint of matter drifting with that expansion. It is one of the closest things cosmology has to a universal calendar. On the largest scales, the universe appears remarkably close to flat. When physicists say space may be flat, they do not mean the universe is a giant flat sheet. They mean its large-scale geometry seems very close to the geometry taught in ordinary school math. Parallel lines tend to stay parallel. The angles of a huge triangle would add up to about 180 degrees. At least that is what measurements currently suggest across the observable universe. There are other possible shapes space could be positively curved, like the surface of a sphere, or negatively curved, like a saddle. But observations of the cosmic microwave background suggest the universe is very close to flat overall. This is one of the reasons inflation became such an important idea. A brief early expansion could have smoothed out any strong curvature, leaving space looking nearly flat across the enormous distances we can observe. A universe can be finite without having an edge. It is possible for something to have a limited size without ending at a wall. The surface of Earth is a simple example. You can travel across it forever without reaching an edge, even though the surface has a finite area. Space may have a similar possibility in more dimensions. The universe could, in principle, curve back around on itself in a way that has no boundary. You would not find a cosmic cliff. You would not reach a final wall where space stops. You would simply keep traveling through a geometry that loops in a way our everyday minds find difficult to picture. Scientists do not yet know the full shape or size of the entire universe. The observable part gives us clues, but it may be only a small region of a much larger reality. The universe is not only expanding, its expansion is accelerating. For much of the 20th century, astronomers expected gravity to gradually slow the universe's expansion. After all, matter pulls on matter, galaxies and galaxy clusters attract each other. So it seemed reasonable to think the expansion should slowly lose momentum. But observations of distant supernovae revealed something unexpected. The expansion of the universe is accelerating over time. Distant galaxies are being carried apart faster and faster on the largest scales. Something appears to be pushing against gravity's attempt to slow everything down. Scientists call the unknown cause dark energy. The name does not mean we understand what it is. It is simply a label for the mysterious effect driving the accelerated expansion. The universe is growing not only larger, but more difficult to keep connected. Dark energy is one of the biggest mysteries in science. Dark energy appears to make up most of the universe's total energy budget, yet nobody knows exactly what it is. It might be a property built into empty space itself. It might be related to the energy of the quantum vacuum. Or it might mean our current understanding of gravity is incomplete on the largest scales. For now, dark energy is a name for an observation. The expansion of the universe is speeding up. Something is responsible, but the true nature of that something remains unknown. It is humbling to realize that the ordinary matter, making up stars, planets, oceans, trees, and people, is only a small part of the cosmic story. Most of the universe may be made of things we cannot see directly and do not yet fully understand. The universe may eventually become darker, colder, and more isolated if dark energy continues behaving the way it seems to now. The distant universe may slowly fade from view. Over unimaginably long periods of time, galaxies outside our local group could be carried so far away that their light becomes too stretched and faint to detect. Stars will eventually burn out new star formation, may slow down. The night sky, seen by far future observers, could look much emptier than it does today. This possible future is sometimes called the Big Freeze. It is not an event that would happen suddenly. It would be a long, quiet thinning of the cosmos. But it is only one possibility. The true nature of dark energy is still unknown, and until we understand it better, the final fate of space-time remains one of the universe's deepest unanswered questions. One reason time feels like it only moves forward is entropy. Entropy is often described as disorder, but it is more useful to think of it as the number of possible ways a situation can exist. A perfectly ordered deck of cards can exist in only a tiny number of arrangements. A shuffled deck can exist in an almost unimaginable number of arrangements. That makes the shuffled state far more likely. The same idea applies to heat, smoke, broken objects, and everything else that seems to move in one direction through time. There are far more ways for heat to spread through a room than there are ways for it to gather itself back into one warm cup of coffee. The universe does not need a conscious force telling things to become messier. It follows probability, and probability may be one of the reasons the past feels different from the future. The early universe had a surprisingly low entropy. That sounds backwards at first. The young universe was hot, dense, and violent. It does not sound especially neat or ordered, but gravity changes the story. A smooth universe, with matter spread almost evenly everywhere, has low gravitational entropy. Over time, gravity gathers matter into stars, galaxies, and black holes. Those structures look more organized to us, but they allow far more possible gravitational arrangements. So, as the universe became clumpier and more complex, its total entropy increased. Why the universe began in such a smooth, special condition is still one of the deepest, unanswered questions in physics. It may be part of the reason history exists at all. Without that low entropy beginning, there may be no clear arrow of time, no lasting memories, and no obvious difference between before and after. The past feels fixed because it has already left physical evidence behind. A memory exists because a brain changed. A photograph exists because light changed a sensor. A footprint exists because a foot pressed into the ground. Every record of the past is a physical change carried into the present. The future has not created those records yet. That is why we can remember yesterday, but not tomorrow. The difference is not only emotional or philosophical. It is physical. Making a record changes something in the universe. Those changes are connected to energy, entropy, and the one-way processes that shape everyday life. The past is full of fossils, scars, old messages, photographs, and memories. The future may contain endless possibilities, but it has not yet written itself into the world around us. On Mercury, the sun rises quickly. On Earth, it takes only minutes. But elsewhere in the solar system, things move much more slowly. On Venus, a single rotation takes longer than its journey around the sun. The planet turns so slowly that one day on Venus lasts longer than an entire Venusian year. Imagine standing on the surface. The sun would crawl across the sky. Days would stretch into months, months into years. The passage of time would feel completely different from what we experience on Earth. The thick atmosphere would block much of the sunlight. The horizon would remain hazy and distant. There would be no familiar blue sky, no clouds drifting overhead as we know them. Only an endless landscape beneath a dim orange glow. The idea of morning would lose much of its meaning. The sun would move so slowly that entire chapters of human life could pass before a complete cycle finished. Somewhere in the Milky Way, a black hole may be moving quietly through the darkness right now. No star is orbiting it. No glowing disk of gas is giving it away. No telescope can simply point toward it and see it. It is alone, a dark remnant of a star that died long ago, drifting between the other stars of our galaxy. Astronomers think there could be millions of black holes like this moving through the Milky Way. Most of them may never be found, not because they are too far away, but because they give off almost nothing. A black hole does not shine. It does not reflect sunlight. And if it is not feeding on gas or pulling material from a nearby star, it can move through space in almost complete silence. For a long time, astronomers mostly found black holes in pairs. A black hole would orbit a normal star. Gas from that star could fall toward the black hole, heat up, and give off X-rays. The black hole itself would still be dark, but the material around it would reveal that something invisible was there. A wandering black hole has no such clue. It may be completely alone, and that makes it one of the hardest things in the universe to find. But in 2011, astronomers noticed something unusual. A distant star near the crowded center of the Milky Way slowly became brighter. Then, over time, it faded back to normal. At first, that might not sound very strange. Stars can change in brightness for many reasons, but this star was not changing by itself. Something invisible had passed between it and Earth. That object did not block the star's light. Instead, it bent the light around itself. The black hole's gravity warped the space between us and the distant star. And for a while, that warped space acted like a giant invisible magnifying glass. The star behind it appeared brighter. Not because the star had become more powerful, not because it had moved closer, but because an unseen black hole had briefly focused its light toward us. This is called gravitational microlensing. A black hole does not always swallow a star whole. Sometimes a star gets close enough to be pulled apart first. Not crushed, not exploded, stretched. Imagine a star drifting through the center of a galaxy. For billions of years, it may have followed a safe path around the dark object at the galaxy's core. Then, after one unlucky change in its orbit, it passes too close. The side of the star facing the black hole feels a stronger pull than the side facing away. At first, the difference is small, but as the star falls closer, that difference becomes stronger and stronger. The black hole begins pulling harder on one side of the star than the other, and eventually, the star can no longer hold itself together. It is stretched into a long stream of hot gas. Astronomers call this a tidal disruption event. It is sometimes called spaghettification, but the name almost makes it sound too simple. This is not a solid object being pulled into noodles. It is an entire star, a sphere of burning plasma, possibly larger than our sun, being pulled into a glowing ribbon by gravity. And there is another strange detail. A black hole does not need to be enormous to do this. In fact, for some of the largest black holes, the event horizon is so wide that a star may cross it before being torn apart in a way the rest of the universe can observe. The star would disappear behind the boundary before its final light could escape. But around smaller supermassive black holes, the destruction can happen outside the point of no return. That means the universe gets to see the final moments. Not directly, not in the way we could watch a planet through a telescope, but through the light released by the star's broken remains. Some tidal disruption events have even revealed something stranger. The star does not always die the first time. In a few cases, astronomers have seen repeating flares from a galaxy's center. A star may pass close to a black hole, lose part of itself, escape, and return again later. Each return strips away more material. Each close pass produces another burst of light, like a star being slowly peeled apart, one orbit at a time. Black holes seem like the closest thing the universe has to forever. They can outlive stars. They can survive the death of entire galaxies. They can sit in the darkness for longer than almost anything else we know. But according to one of the strangest predictions in physics, even a black hole may not last forever. It may slowly disappear, not by exploding like a star, not by being torn apart, but by leaking away, almost unimaginably slowly, into empty space. This idea is called Hawking radiation. It was proposed by physicist Stephen Hawking in the 1970s. At first, it sounded impossible. A black hole is defined by the fact that nothing can escape once it crosses the event horizon. Not matter, not light, not any signal that could carry information back out. So how could a black hole possibly lose anything at all? The answer comes from the strange rules of quantum physics. On very small scales, empty space is not truly empty. Even in the darkest region between galaxies, the universe is never perfectly still. Quantum fields are always present. Tiny fluctuations are always happening. They are too small and too brief for us to see in ordinary life. But near the edge of a black hole, those quiet fluctuations may behave in a very unusual way. But there is another strange part. As a black hole loses mass, it does not cool down. It gets hotter. A smaller black hole gives off more Hawking radiation than a larger one. So for most of its life, the evaporation would be painfully slow. Almost nothing would seem to happen. But near the end, the black hole would shrink faster. Its temperature would rise. Its faint radiation would become stronger. And in the final moment, according to the theory, it could vanish in a brief flash of energy. A black hole that had lasted longer than stars, longer than galaxies, and longer than almost everything else in the cosmos, would finally be gone. No surface left behind, no dark sphere, no empty hole hanging in space, just radiation moving outward into an even older universe. Black holes create one of the biggest mysteries about information. Quantum physics says that information about a physical system should not be truly destroyed. It can become scrambled. It can become scattered. It can become almost impossible to recover. But it should not simply vanish from reality. A black hole seems to challenge that rule. Imagine dropping a book into one. The book has words, pages, atoms, history, and an exact arrangement of information. From outside the event horizon, that detail becomes hidden. Then, according to Hawking's idea, the black hole may eventually evaporate. So, where does the information go? Does it remain encoded around the event horizon? Does it slowly leak out through Hawking radiation? Or does the question reveal that our understanding of quantum physics and space-time is incomplete? Scientists do not yet have a final answer. Somewhere about 250 million light-years away, a black hole is making a sound. Not a roar, not a rumble, not anything a human ear could ever hear. It is playing one note so low that a single vibration takes almost 10 million years to complete. The sound comes from the Perseus galaxy cluster, a vast collection of hundreds of galaxies surrounded by an enormous cloud of incredibly hot gas. Most of space is too empty for sound to travel. Sound needs something to move through. Air, water, metal, anything with particles that can push against each other. The empty space between planets and stars is almost completely silent because there is almost nothing there to carry a pressure wave. But the Perseus cluster is different. Between its galaxies is a huge amount of hot gas. The gas is incredibly thin compared with Earth's atmosphere. But it is still enough for pressure waves to move through it, enough for sound to exist. A black hole can be small compared with the galaxy around it, and still decide what that galaxy becomes. A galaxy may contain hundreds of billions of stars. It may stretch across tens of thousands of light years. It may be filled with gas, dust, planets, and entire solar systems. At its center, there may be one supermassive black hole. From a distance, it seems almost insignificant. A dark object hidden in a galaxy so large that its light can take 100,000 years to cross. But when that black hole begins feeding heavily, it can affect the fate of the entire galaxy. Stars are born from cold clouds of gas. A cloud has to cool enough for gravity to pull it inward. It has to become dense. It has to collapse. And eventually, somewhere inside that collapse, a new star begins to shine. So a galaxy that wants to keep making stars needs cold gas. It needs quiet places where clouds can gather and fall inward. But an active black hole can interrupt that process. When gas falls toward a supermassive black hole, not all of it disappears immediately. Much of it circles around the darkness first. It forms a hot, violent disk. The gas collides. It heats up. It releases huge amounts of energy. And some of that energy does not stay near the black hole. It escapes, sometimes as radiation, sometimes as enormous winds, sometimes as narrow jets that shoot out from opposite sides of the galaxy's center. Before there were stars, there may have been black holes. Before galaxies, before planets, before the first atoms had even formed. In the first moments after the Big Bang, the universe was nothing like it is now. There were no suns in the sky, no empty spaces between galaxies, no planets moving through darkness. The entire universe was unbelievably hot, dense, and bright. Matter and energy filled everything. Space itself was expanding rapidly. And inside that newborn universe, there may have been tiny regions that were slightly denser than everything around them. Not huge differences. Not entire galaxies collapsing. Just small patches where a little too much matter and energy happened to be gathered together. In the universe we know today, a cloud of gas can collapse and become a star. A massive star can collapse and become a black hole. But in the earliest moments of the universe, there were no stars yet. There was only an ocean of energy and matter, and some scientists think that if one region became dense enough, gravity could have caused it to collapse directly into a black hole. No star needed, no supernova, no long life in the sky. Just a dense wrinkle in the newborn universe collapsing into darkness. These are called primordial black holes. Primordial means ancient. It means they would have existed almost from the beginning. And if they are real, they could be older than every star we have ever seen. A black hole can throw a star out of an entire galaxy, not by exploding, not by pulling the star apart, but by using another star as part of a cosmic slingshot. Most stars in the universe do not live alone. Many are born in pairs, two stars orbiting one another through the darkness. They may spend millions of years circling a shared center, held together by their own gravity. From far away, they would look like a single point of light. But up close, they are a tiny private solar system. Two suns locked into an endless dance. Now imagine that pair slowly wandering toward the center of a galaxy. Somewhere ahead is a supermassive black hole. It is invisible. There is no glowing surface to warn them away. No sound. No giant shadow spreading across space. Just a region where gravity becomes stronger and stranger with every passing moment. At first, the two stars continue orbiting each other normally. They are still moving together, still bound, still following the same familiar rhythm they may have shared since the beginning of their lives. But as they pass closer to the black hole, its gravity begins pulling harder on the nearer star than on the farther one. The difference is not important at first. Then it becomes impossible to ignore. The black hole is not simply pulling on the pair as one object. It is reaching into the space between them. And eventually, it can break them apart. One star is pulled onto a new path around the black hole. The other is thrown away, not gently, not slowly, thrown outward at a speed so extreme that it may escape the gravity of the entire galaxy. This is called the Hill's mechanism. Imagine what that journey would feel like from a planet orbiting that star. There would be no sudden explosion, no impact, no great flash in the sky. The star would simply begin following a new path. Its speed through the galaxy would rise. The familiar stars around it would begin drifting behind. The Milky Way would slowly become smaller in the distance, and over millions of years, the entire galaxy could fade into a pale band of light behind it. The star would become a traveler between galaxies, a sun with no home, a solar system moving through a darkness so empty that the nearest stars may be hundreds or thousands of light years away, and the black hole that launched it would remain behind, still invisible, still sitting at the center of the Milky Way, still capable of doing the same thing again. Empty space is not truly empty in quantum physics. In everyday language, a vacuum sounds like nothing at all. No air, no dust, no stars, no matter. But modern physics describes space as filled with quantum fields. An electron can be understood as an excitation in an electron field. A photon is an excitation in the electromagnetic field. Even when there are no particles present, those fields do not vanish. The vacuum is their lowest energy state. That does not mean empty space is constantly making visible particles or offering unlimited free energy. But it does mean that the deepest version of nothing is much stranger than a completely blank void. The darkest space between galaxies still has structure. It still has fields. And those fields help define what can exist there. Even empty space can create a measurable force. When two uncharged metal surfaces are placed extremely close together in a vacuum, they can experience a tiny attraction. This is called the Casimir effect. It does not mean the vacuum is giving us free energy, but it does show that the quantum fields filling space can have physical effects. The exact explanation is more subtle than tiny particles popping in and out between the plates. But the basic lesson is simple. Empty space is not merely a blank backdrop. The quantum vacuum has structure. And under the right conditions, that structure can influence real objects in measurable ways. A quantum object can exist in a blend of possibilities before it is measured. This is called superposition. A particle can be described by several possible outcomes at once, and those possibilities can interfere with each other like overlapping waves. That is why a single particle can gradually create an interference pattern when an experiment is repeated many times. But the large world around us does not seem blurry or uncertain. A chair is in one place. A planet follows one orbit. A cup is either on the table or falling off it. That is partly because large objects constantly interact with their surroundings. Light, heat, air, and countless particles carry information away from them. The delicate quantum possibilities become tangled with the environment and stop behaving like a simple, isolated superposition. The everyday world feels solid because it is never truly alone. Decoherence is one reason the everyday world looks definite. Quantum superpositions are easiest to see when tiny systems are carefully isolated. But in normal life, nothing is isolated. A particle can interact with light, air molecules, heat, vibrations, and countless other particles. Each interaction leaks a little information about the particle into the surrounding world. Over time, the clean interference between different possibilities becomes impossible to observe. The quantum system starts behaving more like an ordinary object with one clear outcome. This does not answer every deep question about measurement, but it helps explain why you never see a baseball in a visible combination of two different places at once. The larger world is constantly tangled up with itself. Entanglement creates connections that are stranger than ordinary distance. Two quantum particles can be prepared in one shared state. Then, even after they are separated, their measurements can show correlations that classical physics cannot fully explain. This does not mean one particle sends a secret message to the other faster than light. The results seen by each observer are still random. Only after they compare their measurements through ordinary communication do the deeper correlations appear. So entanglement does not break relativity, but it reveals that quantum systems can stay connected in a way everyday intuition does not expect. Some physicists think understanding entanglement may eventually help explain the deeper structure of space-time itself. For now, it remains one of the strangest confirmed features of reality. Entanglement cannot be used to send a message faster than light. That sounds disappointing at first. Two particles may be linked across a huge distance, but neither person can choose the result they get when measuring one of them. Each result appears random. The person holding the other particle also sees random results. The strange pattern only appears when both people compare their measurements later, using an ordinary signal that cannot travel faster than light. So entanglement can create deep correlations without becoming a cosmic telephone. The universe still protects cause and effect. You cannot use quantum physics to send a warning into the past, speak instantly to another galaxy, or break the speed limit built into space-time. It does not really make sense to ask what a photon experiences. People sometimes say that, from a photon's point of view, no time passes. The idea comes from the fact that light always travels at light speed. But relativity does not allow a normal rest frame for light. You cannot ride beside a photon, carry a clock next to it, and ask what the universe looks like from there. A clock needs a path through time. Light follows a special kind of path, where the usual measure of elapsed time is 0. That is a mathematical statement, not a photon's personal experience. Photons do not have a point of view in the ordinary sense. Still, it is strange to realize that light can cross billions of years of cosmic history without having a valid rest frame of its own. General relativity and quantum physics do not fully fit together yet. General relativity is our best description of gravity, stars, galaxies, black holes, and the large-scale shape of space-time. Quantum physics is our best description of particles, fields, and the smallest scales of reality. Both theories work incredibly well where they have been tested. But in places where gravity becomes extremely strong and quantum effects become impossible to ignore, the two descriptions stop fitting together cleanly. The center of a black hole and the earliest moments of the universe are examples. Scientists are searching for a theory of quantum gravity that can connect both pictures. We do not have a confirmed final version yet. That gap is one of the biggest unfinished parts of modern physics. The Planck time is not proven to be the smallest possible tick of time. It is an incredibly tiny unit made by combining fundamental constants from gravity, quantum mechanics, and relativity. It is around 10 to the negative 44th of a second. That number is so small that light would travel only an unimaginably tiny distance during one Planck time. Physicists think that around this scale, our familiar picture of smooth space-time may no longer work. Quantum gravity could become important. But the Planck time is not definitely the smallest piece of time. It is better understood as a warning sign. Below that scale, our present theories may no longer be enough to describe what reality is doing. Space-time may not be the deepest layer of reality. General relativity describes space-time as smooth and continuous. Quantum physics describes the universe in terms of fields, probabilities, and tiny interactions. Some physicists wonder whether space, distance, gravity, and even time could emerge from something more basic, like temperature emerging from the motion of countless atoms. In that picture, space-time would not be the stage beneath reality. It would be something reality creates from deeper relationships. Some ideas connect the shape of space-time with quantum information and entanglement. None of this is a confirmed final answer, but it leaves us with a beautiful possibility. The space around you and the time carrying you forward may be part of a deeper pattern we are only beginning to see. What if the Big Bang was not the beginning of everything? What if it was the beginning of something inside something else? There is a strange idea in physics that sounds almost too strange to take seriously at first. The idea that our universe may exist inside a black hole. Not a black hole floating somewhere inside our own universe. A black hole that formed in another universe. A black hole whose interior became everything we know. The stars, the galaxies, the empty space between them. Even time itself. This is not an established fact. There is no evidence that proves we live inside a black hole. But it is a real speculative idea that some physicists have explored. And it begins with a question that is almost impossible to picture. What happens on the inside of a black hole? The universe may be finite without having an edge. That sounds impossible at first. If something is finite, it feels like it should eventually end somewhere. There should be a wall, a border, or a final point where there is simply nothing beyond. But space may not work that way. Think about the surface of Earth. You can travel across it forever without reaching an edge, even though the surface itself has a limited area. In theory, the universe could have a similar shape in more dimensions. You could travel in one direction through space for an unimaginably long time and never find a boundary. There would be no cosmic cliff, no final wall, no place where space suddenly stops. Depending on the true shape of the universe, you might even eventually return to where you started. Scientists do not know whether the entire universe is actually shaped this way, but it means reality may be far stranger than a giant empty room with stars inside it. The universe may have no edge at all, even if it is not infinite. There are parts of the universe we can see that we may never be able to reach. Their ancient light has already arrived here. That is why we can see them. But because the expansion of the universe is speeding up, some of those galaxies are now moving away so quickly that a signal sent from Earth today may never reach them. Their past is visible to us, but their future may be forever out of contact. Imagine looking through a window at a distant island. You can still see the light from its old fires. You can still see what it looked like long ago. But the ocean between you is expanding so quickly that no ship, no message, and no beam of light sent today could ever arrive. The universe contains places like that. Galaxies whose history can reach us, but whose future cannot. The farther into space we look, the more we are looking into a past that may already be permanently separated from us. And maybe that is what makes space-time so strange. It is not only the stage where the universe happens. It is the thing that decides what can meet, what can be seen, what can be remembered, and what may remain forever out of reach. The light around you is moving through space-time. Your memories are moving through space-time. Every star above you is sending a message from another moment in history. And somewhere beyond everything we can see, the universe may continue far past the edge of our knowledge. But none of it needs to be solved tonight. You can let the universe stay enormous. You can let time keep moving quietly forward. And for now, you can simply rest here on this small world, beneath a sky that is older, stranger, and more beautiful than we may ever fully understand. Good night.